Today we are going to begin talking about transient analysis of first order circuits, and this will be one of 3 lectures on this material. Realistically, we can actually cover everything that I want you all to know in 2 lectures, which is usually what I do. And then that 3rd lecture, we work the in-class assignment together, and then I let you guys tackle the lab. So, transient analysis of first order circuits. Okay. So for those of you that have started looking at the practice exams, which I cannot encourage you enough, you should already be doing that. You may have noticed that roughly the last third to half of the circuit analysis problems related to something that we haven't covered yet. This is that thing, okay? So this is going to be a large chunk of your upcoming exam. So if you want to be successful in this class, and also in your later electrical engineering classes where we revisit this topic for second order circuits, etc., you need to really catch what I'm throwing here. Okay. So there are lots of new type words here, even in the title of this thing. Okay, so let's start by talking about what a transient is. So a circuit is considered to be in a transient condition when it is experiencing the effects of a change in the circuit. So effectively, anytime we have a circuit involving a switch, we are going to wind up dealing with a transient analysis problem because the circuit is undergoing some sort of abrupt change that will tend to influence the behavior of voltages, currents, etc., throughout the circuit. Okay. Now let's talk about first order real quick here. I'm not going to write this part down because we're going to kind of adapt our definition as we go through here. A first order circuit is a circuit that has a first order differential equation that governs its behavior. How many of you guys have already taken Math 245? In the process of it. So a very, very small handful of you have had some actual exposure to differential equations. For the rest of you, this will be your first exposure. I will try to make it as painless as humanly possible. And for a first order differential equation, it is actually going to be pretty darn painless. Okay. In the context of circuit analysis, a first order circuit would be a circuit that contains a single equivalent energy storage element. So it can have multiple capacitors or multiple inductors, but they would be able to be simplified down into a single equivalent capacitance or inductance. If we have a circuit like that, it will wind up having a first order differential equation, and therefore it is a first order circuit. Okay. So we're going to start by looking at the transient analysis of what I'll call an RL circuit. So a circuit containing some resistance and some inductance. And the resistance that I'm going to give you here and the inductance that I'm going to give you here could be thought of as the equivalent resistance and equivalent inductance of a larger circuit. But again, it needs to be able to be simplified down into a single R value and a single L value. So let's put this here, analysis of RL circuits. So over here to the right, I'm going to have some resistor value R, and I'm going to connect it to some inductance L, like so. And then let's put a terminal here. I'm going to put a current source along this branch, which will just supply some arbitrary amount of current IS. And then over here on the opposite side, I'm going to have a short circuit. And these three terminals represent effectively a single pole double throw switch, where we might consider this terminal to be A and this terminal to be B. So I would describe this circuit as the switch having been closed at position B for a very long time before closing at position A at t is equal to 0. Okay, so our switch is rotating the way that I've depicted it counterclockwise so that the current source is going to wind up being disconnected from that RL network on the right-hand side after the switch actuates. We are going to have to pay attention to what's going on at multiple different intervals of time in order to get a good understanding of what's going on here. So I'm going to define a few things. The first thing that I'm going to define is my inductor current. And this is going to be the most important quantity that we're going to look at for these RL circuits. I'm also going to define the voltage drop across my inductor, positive polarity on top, and this might seem odd, but I'll explain my reasoning shortly. This will be the voltage drop across my resistor, positive polarity on bottom. The reason I chose to have the resistor's positive polarity terminal on bottom is so that after our switch changes state, any current that's flowing in the inductor winds up flowing into the positive polarity terminal of the inductor and the resistor. So I'm going to get positive signs everywhere when I write my differential equation for this particular circuit. Okay. So let's talk about what this circuit looks like at t is equal to 0. And let's say t is equal to 0 minus specifically. So what do I mean by t is equal to 0 minus? Does anybody have any idea? Exactly right. So t is equal to 0 minus represents the instant in time immediately before the switch changed states. So before it switched over from being closed at position B to being closed at position A. Transversely, t is equal to 0 plus, which we'll talk about in a moment, is the exact opposite. It is the moment after the switch changed states. Okay. So for t is actually, let me put this a slightly better way, less than or equal to 0 plus, our circuit is at DC steady state. Okay. So for all time less than or equal to t is equal to 0 minus, we can treat this circuit as if it were a DC circuit. Okay. So if I wanted to analyze this circuit at t is equal to 0 minus, it would look something like this. Where I'm going to actually, what should inductor look like in a DC circuit? Short circuit, absolutely right. This is my current at t is equal to 0 minus. This is the voltage drop across my inductor at t is equal to 0 minus. This is the voltage drop across my resistor at t is equal to 0 minus. So how could we solve for any of these quantities? Not to be rude, but this is literally as simple as it gets. I was expecting an answer by now. Walker. So Walker says that VL at 0 minus is 0 volts. That's very true. The voltage drop across a short circuit is always 0. And since our inductor is being represented by a short circuit, the voltage drop across our inductor must then be 0. I agree with that wholeheartedly. What about the other two quantities, our inductor current and our resistor voltage? Absolutely right. So Carson says that IL at 0 minus will just be IS. That should be fairly obvious. The inductor, since it's acting as a short, shorts out that resistive path so that all of the current will flow through the inductor, none of the current will flow through the resistor. So I'm on board with that. Our last quantity then is the voltage drop across our resistor. What should that be? Also 0 because it's in parallel with the short circuit. So let's talk about what the consequences of these initial conditions on this system are, okay? If the current flowing through the inductor is non-zero, then that means the inductor has some amount of energy being stored inside of it, right? Because we know that the energy stored by an inductor is 1/2 times the inductor value times the current squared. If the current is non-zero, there is energy stored in the inductor, okay? So that's the situation that we have going into the moment in time before the switch changes states, right? Immediately after the switch changes state, so let's call this, so for 0 plus is less than or equal to t is less than infinity, and that might seem like a weird thing to put it that way, and why don't I just call it t greater than or equal to 0 plus? And because infinity has a special meaning in these types of circuits that we're going to talk about here. So for this region of time, or interval of time, our current source is now just, excuse me, feeding the short circuit, and my RL network has been effectively disconnected from that source. Since we're no longer at DC steady state, and I'm going to actually explicitly say this is when our transient condition occurs, we should see, sorry, let's just call this IL of t, VL of t, and VR of t like so. So what's happening during this interval of time, right? Our inductor had some amount of stored energy. What do resistors do? Think about what we talked about on, I believe, the 3rd day of class. They do. They definitely impede the flow of current. There we go. They convert electrical energy into heat energy, okay? So all the resistor in this circuit is going to do is gradually convert all of the energy that was stored by the inductor into heat. And that process takes time, okay? So a very, very long time after the switch has closed, which we would call t is equal to infinity, we're going to be at DC steady state again, right? So let's call this for t greater than infinity. And I know that seems odd, but we'll talk about that. So a long time after the switch changes, and this will once again look like a DC steady state condition. Our circuit is going to look like this. This is going to be IL at t is equal to infinity, VL at t is equal to infinity, VR at t is equal to infinity. And I would like for you guys to tell me what the values of IL, VL, and VR are for this case. What was that? So, but not all of them were zero before. VL will be zero since it's the voltage drop across a short circuit. Again, absolutely right. So VL at infinity is going to look like 0 volts. VR at infinity is also going to look like 0 volts because the resistor is still in parallel with that inductor. And so if the voltage drop across the inductor was 0, the voltage drop across the resistor has to be 0. What's our inductor current going to be? So let me ask you guys a question. How can the inductor have any current flowing through it? There we go. So this point in time represents after all of the stored energy by the inductor has been converted into heat by the resistor. If the inductor has no more stored energy, then the current flowing through that inductor has to be 0 amps. And we could bear this out simply by applying Kirchhoff's current law, right? So what I mean by that, we can observe that we have IS current flowing up and IS current flowing here. So how much current is flowing to the right to ever make it towards the inductor at all? Literally none. So once again, that source is disconnected from the resistor inductor network. And so once all of that stored energy gets converted into heat, we shouldn't see any current flowing through either that resistor or that inductor. Okay. All right, so I'm going to draw a graph here. So this is our inductor current as a function of time. And just for the sake of argument, I'm going to call this point in time out here approximately infinity. So what we would see is that our inductor current would have some fixed value all the way up to this point where t is equal to 0, right? And this value would simply be IS. And once again, in this region of time, we are at DC, steady state. We also know that for all points in time greater than t is equal to infinity, our inductor current should be 0. We'll put a dashed line up here, and everything to the right of this infinity is also a DC steady state condition. And then here in the middle is where we have our transient condition. We didn't solve for what that current looks like over that interval yet. So what we're going to be doing next is using a little bit of calculus to effectively develop a mathematical model that tells us what happens in between those two DC steady state conditions, okay? So if we go back to this circuit over the interval 0 plus is less than or equal to t is less than or equal to infinity, I'm going to write a simple Kirchhoff's voltage law equation around that loop, right? So during the transient condition, I know that VR plus VL must sum together to make 0 volts. And once again, let me scroll back up here so you can see it. That is just me applying Kirchhoff's voltage law around that right-hand loop containing our resistance and inductance. Okay. Now, luckily for us, we can express both of those voltages in terms of that inductor current, right? So how do I express the resistor voltage in terms of the inductor current? That's just Ohm's law, right? So it'll just be R times IL of T. How do I express the voltage drop across my inductor in terms of inductor current? Exactly right. L times the derivative of my inductor current with respect to time. This guy right here is based on who raised their hands earlier. The first differential equation most of you have seen. This is what's known as a linear, homogeneous, first order differential equation. The only parts that really matter to you guys are that it's linear, because we're dealing with linear circuits in this class, and that it is a first order differential equation. Okay. So, for those of you who have not had Math 245, which means you don't know what the answer to every linear first order differential equation is, let's talk our way through some things here, okay? So what our goal is to come up with an expression that describes IL of T that will satisfy this equation. So let's think about what that expression has to look like, okay? So I have something to where a coefficient, in this case my resistor value, multiplied by some function plus some other coefficient times the derivative of the function have to add together to make 0. So what function do we know of where the function itself and the first derivative of the function have the exact same form? You've had the class before, you're cheating. Somebody else. Yeah, an exponential function, right? So an exponential function, the first derivative of an exponential function is an exponential function. So we are going to make an educated guess and say that our inductor current will be of the form AE to the ST, where A is just some coefficient that's scaling that exponential function, and we'll talk about how to figure that out as well. And that coefficient S is telling us the rate at which our exponential function is either going to be increasing if S happens to be positive, or decreasing if S happens to be negative, okay? So we're going to use this guess value, this very generic guess value, and plug it in to our differential equation and kind of see what shakes out. So that would look like R times A e to the st plus SL times A e to the st must equal to 0, if I did my derivative correctly, and I feel pretty strongly that I did. Now I'm going to just group some terms together, right? So we can see that both terms have a factor of A. Then I'm going to have R plus SL times e to the st is equal to 0. Now, under what conditions will this last equation be equal to 0? Well, the first and most obvious thing would be if A is equal to 0, then my equation is equal to 0. That is a solution to this, but it is a trivial solution because it effectively describes a situation in which the inductor didn't have any stored energy to begin with. So if we never connect the inductor to that current source, then we'll always have the inductor current is equal to 0. It is true, but it doesn't really provide us a lot of information about the system that we are looking at. What if we look at that rightmost term, e to the st? When will that be equal to 0? It'll never get all the way down to 0. If s is negative, it will approach 0 after a very long time, but that's still not particularly helpful. So instead, we need to look at this middle bit right here, which is known as the characteristic equation for the system. So what value of S will force this equation to always equal 0? Okay, so it does have to be negative. Negative R over L. Absolutely right. So when S, which is the natural frequency for this system, is equal to negative R over L, our differential equation will always be equal to 0. So we are going to modify this equation here to now say A e to the negative R over L times time. So we figured out what S is for this system. That's great. Now we need to figure out what A is. So what do we know in particular about inductor currents and how they're allowed to change? Not abruptly, right? So if we go back to this graph, we see that at the instant in time before our switch changes states, t is equal to 0 minus, our inductor current has a value of IS. So what does the value of the inductor current have to be at t is equal to 0 plus? IS, because it cannot change abruptly, okay? So if we were to evaluate this function at t is equal to 0, we would have, do this here, IL of 0 is equal to A e to the 0, or just A, which means that coefficient A is simply the initial condition on the inductor current. I'm going to explicitly state this as IL at 0 minus e to the negative r over L times time. For an inductor in particular, it literally doesn't matter if we use 0 minus or 0 plus because it's the exact same thing. But for other circuit elements, it does make a distinct difference. Actually, realistically, I should put that at 0 plus, sorry. And the reason why I should put it at 0 plus is A, I forgot something important, and B, we're doing this during the transient condition, which starts at t is equal to 0 plus. So that's a better argument than I forgot. So this mathematical description describes the behavior of the inductor current in literally every first order RL circuit. We did not use numbers or anything. We derived this generically so that we could apply it towards literally anything that we do. So what I'm going to do now is I'm going to open up our in-class assignment and let's look at one of those problems. So if I'm remembering correctly, this would be in-class assignment number 13. And this first problem here looks like something good that we could work on, okay? So while we work our way through this, I'm going to teach you kind of an algorithm or process by which to do these things. Okay. So our first step will be to analyze the circuit at t is equal to 0 minus. So in this particular circuit, our switch has been closed for a long time before opening at t is equal to 0. So at t is equal to 0 minus, our switch is going to look like a short circuit. So we'll have our 18-volt source, short circuit, our 4 kilo ohm resistor. Our inductor is going to look like a short circuit because we are at DC steady state. And down here we have our 8 kilo ohm resistor. And our two quantities of interest are our inductor current, I of 0 minus, and this resistor voltage, V of 0 minus. Now, I understand that the answers are literally in front of you, but let's ignore those and apply circuit analysis techniques to figure out what those two quantities would be. So, would anybody care to take a stab at either of those quantities? Yes, ma'am. So I don't think current division is necessary or technically possible here. The reason why I say current division isn't possible is because we don't know the amount of current that is dividing between those two parallel paths. Voltage division is also not feasible because our resistors are in parallel with the voltage source, so there's no division going on. It's okay. All right, so Ian suggests that our voltage at 0 minus is just 18 volts because that resistor is in parallel with an 18-volt source. Absolutely correct. So we got that answer completely by inspection. No need for any real circuit analysis whatsoever, other than understanding that things that are in parallel have the same voltage drop across them. How do we find I at 0 minus? just Ohm's law. Right, so thank goodness nobody said mesh. So Ohm's law, we would have 18 volts divided by 8 kiloohms. So 18 over 8 looks like 9 over 4 milliamps. Anybody have any questions, comments, or concerns regarding the analysis, and I use that term loosely, we did here? All right, so this was fairly straightforward. Now we are going to analyze our circuit. At t is equal to 0 plus. So this is the moment in time after our switch change states, okay? And I'm going to do something that's going to seem a little bit wonky, and we'll talk our way through it here momentarily. Because this is after our switch opened up, our switch is going to look like an open circuit. Here is our 4 kilo ohm resistor, over which we are going to be finding the voltage V at 0 plus. Over here on the right-hand side is our 8 kilo ohm resistor. And I'm going to make a note out here that I of 0 plus has to be I at 0 minus, because it is an inductor current and it cannot change abruptly. So I've intentionally left my inductor blank or not in the circuit because I want to talk about what we are going to represent the inductor as. Okay? So this specific diagram is representing the circuit at a very specific point in time. T is equal to 0 plus, okay? So at t is equal to 0 plus, we know that the current flowing through the inductor is a fixed quantity. It cannot have changed from what it was at t is equal to 0 minus, because in order for it to have changed, we would have had to create or destroy charge or transfer an infinite amount of energy. Can't remember which one, but either way, it's bad news bears. So what type of circuit element do we know of that provides a fixed amount of current? A current source. So we are going to represent our inductor at this specific point in time as a current source. And our current source will have the same direction as IL, and it will have the same magnitude as IL at 0 minus. So that's going to look like a 9/4 milliamp source. So let me repeat this. At t is equal to 0 plus specifically, this is the only point in time this will be true, our inductor can be represented by a current source, where that current source will have the same magnitude and direction as I at 0 minus. So how do we find that voltage V at 0 plus? Ohm's law again. So tell me what my equation should look like, Christina. Negative 4 kiloohms times 9/4 of a milliamp, which would equal negative 9 volts if my mental math works out correctly. Does anybody have a problem with that equation? I personally do not. She correctly observed that the current is flowing into the negative polarity terminal, which is why we would have a negative sign out here, and it's just Ohm's law, so I times R is equal to V. Yes, sir. That's exactly right. And we're looking at this literally the instant in time after the switch changed state. So it's still T is equal to 0. It's just after the switch changed, right? So because our inductor current cannot change abruptly, if our inductor current has some value at T is equal to 0 minus, it has to have the exact same value at T is equal to 0 plus. If it doesn't, we have transferred an infinite amount of energy, which cannot happen. All right, so any other questions about our analysis at T is equal to 0 plus? So I'm trying to decide if I want to do the analysis at T is equal to infinity. Let me explain myself a little bit. What we're doing today is effectively what's called the natural response of the system. So this is how the system behaves when you take sources away from your energy storage elements. Okay. What we're going to be looking at on Friday's class meeting is the total response, which includes what's called the forced response. And the forced response is what happens when we add sources into our system. Okay. When we have forced response problems, the value at T is equal to infinity might not be 0. For a natural response problem like this, the value at T is equal to infinity will literally always be 0. So if we wrote it down, we would be finding out that the answer is 0, which is arguably a waste of time, but it would make the process for the two different types of circuits consistent. Okay. So I'm going to put step number 3 here in a different color, and we're not actually going to do it. And this is just priming you for what we're going to be doing on Friday. So step number 3 would be to analyze the circuit at T is equal to infinity. Like I said, we're not going to do it. We would simply observe, in this case, that I at infinity must be 0 amps, and V at infinity would wind up being 0 volts. Once again, it's because we disconnected our source. All right. So step number 4, we are going to determine REQ and LEQ during the transient condition. Okay. So I'm going to ask you guys an incredibly tough question. What should LEQ be? Yeah. Absolutely right. So the equivalent inductance of this circuit, LEQ, is equal to 12 milliohms. Now, to determine REQ, there is a special process that we are going to do. We are finding the equivalent resistance seen by our energy storage element during the transient condition. Okay. So I'm going to draw my circuit during the transient condition. Was that 18? Yeah. Here's my inductor. I'm just going to call it L because I'm going to wind up erasing it in a moment anyway. Okay, so we're finding the Thevenin resistance. So what do we do when we find the Thevenin resistance? We need to be looking at a dead network, right? Which means this 18-volt source is now a short circuit. We're finding our Thevenin equivalent resistance with respect to our energy storage element, which in this case is our inductor. So we take the inductor out and we look in through the terminals left behind by the inductance. What resistance do we see? 12 kiloohms, right? Just those two resistors in series. Does it matter that there's this dangly bit of wire over here? No, not at all, right? So Req is just 12 kiloohms, 4 kiloohms plus 8 kiloohms. All right, I'm running out of space down here. So let's go above the circuit, maybe. This last step is very easy. Okay. So this will be step number 6. Oh, well then step number 5, my bad, I just can't count. Plug stuff in to our equation. Okay. So IL of t, or I of t, I guess, for this particular case, is going to look like this, right? So it's going to be IL at 0 minus for t less than 0 minus, and it will be IL of 0 plus e to the negative REQ over LEQ times t for t greater than or equal to 0 plus. That's literally the relationships that we derived a little while ago. Okay. So what was IL at 0 minus? If I'm not mistaken, it was 9/4 of a milliamp. And then we would have 9/4 e to the negative. So let's see. So R was 12 kiloohms. LEQ was 12 millihenries. So what's that ratio going to look like? Times 10 to the what? Times 10 to the 6, right? Because 10 to the 3 divided by 10 to the negative 3 is going to look like 10 to the positive 6. So that's what our current is going to look like. And I literally just plug stuff in to this equation that we developed here, specifically using REQ and LEQ for this particular system. Okay. Now, that isn't the only thing that you were asked for on this one. So we figured out I of t. Now we need to figure out V of t. Hold on. Why is that? There we go. So how might we go about figuring out V of t? Well, let's look at some things here. I'll try to sneak it in here. We could, or actually, I'm not entirely sure that we would need to, but we could if we wanted to. We're going to have a piecewise function, so it's going to behave in a particular way for t is less than 0 minus, and then it's going to behave in a different way for t is greater than or equal to 0 plus. So what we could do, not saying this is what we're going to do, but this is what we could do. We could observe that during the transient condition, our current I of t is flowing into the negative polarity terminal of our 4 kilo ohm resistor and literally just use Ohm's law, right? So that would be one way to do it. So we could have, let's see, so this should be 18 volts up here and then negative 9 e to the negative 10 to the 6 t volts, like so, where that is literally just the combination. This part right here is just I of t times negative 4 kilo ohms, right? That is one way that we could do it. Now I want you guys to notice something here. The form of our resistor voltage is of the exact same form as our inductor current, which makes sense because Ohm's law kind of tells us that it has to be, right? So if the form of our resistor voltage is the same form as our inductor current, what do you think the form of the inductor voltage is going to be? Well, according to Kirchhoff's voltage law, if I have to add all those things together to make 0, it's also going to be an exponentially decaying voltage. What about the currents through our resistors? Well, they're the same thing as the inductor current, so they're also exponentially decaying currents. So effectively, in a system like this, during the transient condition, if one thing is exponentially decaying, everything is exponentially decaying, and they're all decaying at literally the exact same rate. Okay. So we can come up with a generic equation. Let me do this over here in the notes thing, right? So our generic equation will be as follows. Y of t, where Y represents any current or voltage in our system, will be of the form Y at 0 minus for t less than 0 minus, and Y at 0 plus e to the negative r over L times time for t greater than or equal to 0 plus. Every current and voltage waveform in our system will behave in this way because Kirchhoff's voltage law, Ohm's law, and Kirchhoff's current law literally force them to. That's the only way the math works out. And if we made a circuit like this and connected it to an oscilloscope so that we could see how the function varies over time, we would literally see that every voltage and every current in this system will be an exponentially decaying thing. So instead of using Ohm's law to get this result, we could literally get the exact same thing. This negative 9 volts right here is exactly what we got for V at 0 plus. This 10 to the 6 bit right here is exactly the ratio of R over L that we determined earlier. Everything is going to behave this way. So instead of actually having to think about how the things are related, we get to just plug it into the generic equation and call it a day because it's always going to work out that way. So before we move on, any questions about this particular problem? Process seemed fairly straightforward. Analyze the circuit at t is equal to 0 minus. Analyze the circuit at t is equal to 0 plus. Possibly analyze the circuit at t is equal to infinity. And we'll talk about what specific conditions need to happen for that to be a thing. Determine the equivalent inductance. Determine the equivalent resistance. Plug stuff into our generic equation. We've done it correctly. Yes, ma'am. So the short answer is yes, but I won't give you any problems that have dependent sources for this class. Circuits 2, folks that go on in electrical engineering, you bet your butt they'll be there, but not circuits 1. Honestly, it isn't any harder or any difficult because you already know how to find the Thevenin equivalent resistance of a circuit that contains a dependent source. But for whatever reason, I got pretty significant blowback from not only students, but faculty when I was putting dependent sources in my transient problems. So I kind of stopped for now. So for now, yeah. As I dominate this series with an iron fist, I might retake that as an option, but not this year. Yeah. Yes.
Whenever you with that door, whenever you redrew the right, you said it was look at it as a transient condition. So that actually zero plus.
So for exactly right. So that's why I didn't specifically say at 0 plus, but 0 plus would work. The reason why I don't specifically say 0 plus is because I want you to take the inductor out, and if you don't see the inductor, you don't, like if you had replaced it with the current source, it might not be obvious as to which element you're supposed to take out. But that current source is representing the inductor. So definitely not at t is equal to 0 minus though. That is one of the most common mistakes that I see students make, is they try to find the equivalent resistance at t is equal to 0 minus, and that doesn't mean anything because that's not during the transient condition, and we're explicitly trying to find the resistance during the transient condition so that we can define the rate of decay during the transient condition. All right, any other questions about this? Okay, so we have bent RL circuits to our will, and we arguably have some understanding of how they are going to behave. Now let's look at RC circuits, and this derivation will be a lot quicker because it's pretty much the same thing. So let's say that I have the following circuit where I have some voltage source connected to a switch. This switch is going to open at t is equal to 0. And then I have some resistance R and some capacitance C connected to each other. I am going to define my capacitor voltage VC like this so that we can see it's the same voltage drop across both the resistor and the capacitor because they are in parallel. I'm going to define my inductor current IC as flowing down, and I'm going to define my resistor current IR as flowing down. So without going into as much detail as we did a while ago for the RL circuits, what would this circuit look like at t is equal to 0 minus? We'd have a voltage source in parallel with a resistor in parallel with an open circuit, because the capacitor is going to look like an open circuit at DC steady state. What would the voltage drop across that capacitor be? Vs. Since the capacitor's voltage is non-zero, that means the capacitor has some amount of stored energy. So during the transient condition, the capacitor is going to slowly discharge as its stored energy gets converted into heat by that resistor R. So it's going to be the same process, but now it's capacitor energy being converted into heat as opposed to inductor energy being converted into heat. So what is our differential equation going to look like during the transient condition? Well, we could say that our resistor current IR plus our capacitor current IC must sum together to make 0. That's just Kirchhoff's current law. I can express each of those currents in terms of my capacitor voltage. So that would be 1 over R times VC plus C times the derivative of my capacitor voltage with respect to time is equal to 0. And once again, I have a linear first order homogeneous differential equation. We already know that the generic solution should be AE to the ST. If it worked last time, why wouldn't it work this time? And so putting that in, we have 1 over R times AE to the ST plus SC times AE to the ST is equal 0, or A multiplied by 1 over R plus SC times E to the ST is equal to 0. What value of S will ensure that this equation is always 0? S is equal to negative 1 over RC. So what we'll find is that VC of t will be VC of 0 plus e to the negative t divided by RC. So this is what our form is going to look like. And then generically, for these RC circuits, y of t will be y of 0 minus for t less than 0 minus y of 0 plus e to the negative t divided by RC for t greater than or equal 0 plus. Went through that one much quicker because once again, it is literally the exact same derivation. We're just using a slightly different differential equation. So how do you think our process for solving these circuits is going to change when we have a capacitor? Pretty much it's not. The only difference is whichever one where we're calculating LEQ and REQ, we now calculate CEQ instead of LEQ because there isn't an L. Everything else is literally the exact same thing. Okay? So let's pop back over to the in-class assignment and work a problem that has a capacitor in it. So this particular problem brings up something interesting about our process here. For this problem, you are asked to solve for just the current IR of t. However, you literally cannot do that if you aren't keeping track of what the capacitor voltage is also doing. Because the capacitor voltage is going to influence the behavior of the circuit during the transient condition. So even though you're not specifically asked for it, we also need to keep track of this voltage VC of t at least at certain points in time. So what's step one supposed to be? At t is equal to 0 minus. Absolutely right. So at t is equal to 0 minus, our switch is going to be closed. And so we're going to have 2 kilo ohm resistor, this 4 kilo ohm resistor, this 4 milliamp source, one kilo ohm resistor, 2 kilo ohm resistor through which a current IR at 0 minus is flowing. And then out here to the right, I'm going to have an open circuited set of terminals over which I will need to determine VC at 0 minus. So how might I go about finding either of those quantities? So the voltage drop across the 2 kilo ohm resistor is indeed the capacitor voltage. So that is definitely one way to do it. How would we find the voltage drop across the 2 kilo ohm resistor? So current division will get us the current flowing through the resistor, and then we could use Ohm's law to that result to get the voltage. So I think that's a reasonable way to do it. So IR at 0 minus using current division is going to look like 4 milliamps times 1 over 1 kilo ohm plus 2 kilo ohms divided by 1 over 2 kilo ohms plus 4 kilo ohms plus 1 over 1 kilo ohm plus 2 kilo ohms. So to be clear here, I'm really just lumping these two resistors together into a single equivalent resistance of that branch that's in parallel with the current source. And I'm lumping these two together as a single equivalent resistance that's in parallel with that current source. And that's what's allowing me to apply current division to this system. Are we clear on what I'm throwing there? Okay. So if we plug these results into our calculator, believe we get 8/3 of a milliamp. Let's see, 1/3 over 1/3 plus 1/6 is 1/3. Excuse me, 2/6 over 2/6 plus 1/6, so 2 over 3. 2 over 3 times 4 milliamps is 8/3. Yeah. All right. According to Carson, and he is correct, we could then use Ohm's law to determine VC at 0 minus, which would literally just be 2 kilo ohms times 8/3 of a milliamp would give us 16/3 of a volt. Any questions about the analysis we carried out there? The capacitance? Okay, so the capacitance is going to look like an open circuit at DC steady state. And anytime we're analyzing the circuit at T is equal to 0 minus or T is equal to infinity, we are at DC steady state. No problem. Any other questions about this analysis? Okay, so what are things going to look like at T is equal to 0 plus? Let T is equal to 0 plus, our switch is now an open circuit, which means everything to the left of this dashed line is no longer connected to our resistor and capacitor network on the right-hand side, right? So we would have 2 kilo ohms, 4 kilo ohms, 4 milliamps, 1 kilo ohm. The open circuit I'm drawing here represents our switch. Here is our 2 kilo ohm resistor through which a current IR at 0 plus is flowing. What do you guys think our capacitor is going to look like? So once again, we're analyzing this circuit at T is equal to 0 plus. We know that the capacitor voltage cannot change abruptly. So VC at 0 plus has to be equal to VC at 0 minus is 16/3 of a volt. What circuit element do we know of where the voltage is a fixed quantity? A voltage source. Absolutely right. So our voltage source is going to have the same polarity and magnitude as VC at 0 minus. So we would have 16/3 of a volt source here. What is IR at 0 plus then? So 16/3 of a volt divided by 2 kilo ohms gives us 8/3 of a milliamp. We will not need to do the analysis at T is equal to infinity for this particular problem, so I'm just going to completely skip that step. So now we need to figure out CEQ and REQ. So what's CEQ going to be? Looks like 300 microfarads because it's literally the only capacitor in the circuit. So that's pretty low hanging fruit. To determine REQ, once again, we're going to be looking at our dead network during the transient condition. So I'm going to do this over here. Here's our 2 kilo ohm resistor, our 4 kilo ohm resistor. Our current source is going to look like an open circuit. We also have an open circuit from our switch. Here's our other 2 kilo ohm resistor. And then these open circuited terminals to the right represent where the capacitor was. So these are the ones that we're looking into. What equivalent resistance do we see? 2 kilo ohms, that's it. Putting all of this together, IR of T will be equal to 8/3 of a milliamp for T less than 0 minus 8/3 e to the negative. All right, so let's do some math here. So CEQ times REQ, 300. Let me grab a calculator. So 300 microfarads times 2,000 ohms gives me 0.6 seconds, or 3/5 of a second. So if I flip that number over, it'll be 5/3 T milliamps for T greater than or equal to 0 plus. Since our generic equation says that it's supposed to be 1 over RC, if I take the product of R and C and then take the reciprocal of that, that's what the coefficient on T will be. All right, so we've worked a problem with an RL circuit and an RC circuit. So I'm going to leave problem 3 up to you guys.